All right, so I think I can do the introduction. So hello everyone, welcome to the first talk in the sustainability seminar series. I'm very happy to introduce Ricardo Bianchini. So he's going to tell us about the challenges and work that Microsoft Azure is doing in sustainability, given specifically the newer AI workloads. So Ricardo and I met years ago when I was interviewing for Microsoft Research, and I am actually very excited to hear what's been going on in Azure. He's a technical fellow. He has won many awards over the time, too many to list. And I am really excited to have him with us today. So, Ricardo, I'll leave it to you.
All right. Thank you so much, Oana, and thank you all for attending. Thank you for inviting me, especially as the first talk of the seminar. It's like a big honor, right? I hope I don't disappoint too much. So like Oana said, I'm going to be talking about challenges and opportunities in power and sustainability. And this, I would say, is the beginning of the AI era. These are some of my collaborators from my own group, both in research and production, but we have many collaborators across other parts of Microsoft and in academia as well. So let me start with an outline of what I'm going to talk about. So I'll start with some macro trends that I see today, right, as this era is starting. In terms of power demands and in terms of what's happening in terms of hardware and so on. Then I'll talk about in more detail in terms of the three layers of the compute stack, the AI platform software, the hardware, and the physical infrastructure, where we are and some of the challenges that I see ahead. Then I'll talk about one particular technique that we worked on that I find interesting and sort of we can simplify for a presentation here that I think is interesting and goes towards the direction of mitigating some of these problems. And then I'll talk about some research opportunities that are out there for the taking, right? So let me start with these macro trends. And first, talking sort of very high level about what's going on, right? We have two main conflicting goals, right? One is because of the climate crisis and so on, we want to reduce the number of resources we consume. We want to reduce the carbon emissions. But at the same time, a conflicting goal is to popularize AI, right? To make life better, right? Society better by using AI, make people more productive and so on. However, that increases resources and emissions, right? And in fact, this started out so quickly and so strongly that it's more like this, right? The need for resources is skyrocketing. So there's a conflict there, right? Now, how do we manage this conflict, right? There are many things that are going on and like people are working on, right? At the level of the AI models and different optimizations like quantization, pruning, you name it, right? There's a lot happening in that space. Sort of a mix of experts, types of models and so forth. Then, do you see my mouse? You see my mouse, right? Yeah, then you see at the level of the compute stack, the software, hardware, and physical infrastructure, there's a lot of work on efficiency, and we need more work there. So I'll talk more about this. Then there are sort of approaches on component reuse, maybe sort of decommissioned hardware. We're looking at sort of materials. Folks Then clean energy, right? You've seen basically all the hyperscalers talking about nuclear power, right? But there's also sort of across the supply chain, right? We need everybody to clean up their act, right? And there's much more, right? And I'm not an expert on all these areas, but the nice thing about the conjunction of them, and in anyone specifically, there's a new era of innovation going on, right, across all of these spaces. And this is super exciting, especially for PhD students in computer science, electrical engineering, and so on, because there are a lot of opportunities in software, hardware, and physical infrastructure efficiency. And this is what I'm going to focus on. Those are the things that I know a little more about, right? So let's look first in terms of the macro trends, in terms of model sizes and their computational needs, right? So some of you may have seen this graph before. On the x-axis, we see time in years, right? This is 2022. On the y-axis, you see a log scale of floating point operations to train these different models, right? So what you see here is like an exponential increase, right? And very, very fast. You see more and more models coming out. And this doesn't even include the latest models, right? You see Palm here is a 540 billion parameter model, but GPT-4 and Gemini Ultra, for example, are expected to be in the trillions of parameters, right? So we're way off this graph here already, right? And it looks like this is going to continue for the foreseeable future. And what's interesting is that you think, oh, this is an enormous amount of computation requirements, right, for these models. Turns out that turns out that inference is going to be a much bigger thing than training, right? Because companies typically cannot monetize training. They can only monetize inference. So if you don't have an enormous inference infrastructure, how are you going to be able to afford the training one, right? So inference is going to be much bigger in terms of its computational requirements. So this is sort of giving numbers to what I was talking about before, sort of the incredible needs, computational needs of AI. So now let's look at the electricity demand that increase, and people were projecting enormous increases in electricity demand. So this graph here is from SemiAnalysis. On the x-axis, again, I show time in years, right? On the y-axis on the left, it's what percentage data centers are of global power generation or power demand. And on the right side, it's the amount of power that data centers will consume or expected to consume. These predictions were made in 2023. And so we don't know exactly where things are going to land, but it's pretty clear. A few things are very clear, right? Even in this base case here, the blue line, dark blue line, we would get to 2030, so just 5 years from now, at 171 gigawatts for data centers worldwide. We're now today at roughly 55. So this is like a 3x increase in just 5 years, right? And if you assume the accelerated case, like if AI really takes flight and gets extremely popular, then we're talking even higher, right? We're talking 242 gigawatts, right? So these are enormous increases in electricity consumption by data centers. So it's a problem, right? How do you provision all of the electricity? How do you make it all sustainable and so on, right? What's interesting too from this graph is that you see here on the left that efficiency was pretty good at keeping electricity consumption within check, the electricity consumption by the cloud, right? The cloud grew much more than this rate here, right? But efficiency improvements with virtualization, the cloud, improvements in PUE for both cooling overheads and power delivery overheads. PUE meaning power usage efficiency. If I'm sort of assuming too much, please feel free to stop me. But you see here, right, that we were able to keep the curve sort of in check. We're going to need something like that going forward, right? Because this is really going to be tough to provision all this and to be able to keep it in such a way that it doesn't put us in a big hole in terms of sustainability. What's interesting, everybody talks about DeepSeek, right? And how efficient it was and so forth. But there's something well known in economics called the Jevons paradox. What that means is that when you make things more and more efficient, it doesn't reduce their use. It actually increases their use because it's more accessible to more people. And this has happened in history many, many times. For example, wide body airplanes, right? When you made the airplane really wide so that you could fit many more people, that didn't reduce the number of people who were flying because it made flying much cheaper. So more people wanted to fly, right? So things like that, right? Advances that improve efficiency tremendously will increase that, likely increase that amount of power we're going to need, right? So you might say, well, then don't make any efficiency improvements. No, right? Because you want more people to use it, right? This is a good thing for society, right? At least if we handle it well. So you want both things at the same time, right? So we need to work on efficiency so that we do something more like this, where the use grew much more, but we kept it in check. It's going to be much harder than the first time around, by the way, just to be clear. So what's happening in terms of, again, macro trends in terms of server shipments? And you see, again, a graph showing time on the x-axis and millions of units shipped. And these are servers of different industries or different categories. And you see all of them are roughly flat, right, going forward in terms of these predictions. Predictions were made in 2023. But you see the only one going much higher up is shipments of GPU-based servers. And again, its inference is expected to grow at a 17% annual rate, whereas training is expected to grow at a 5% annual rate, right? So again, you see a significant increase there. Of course, these are all predictions, right? 5 years from now, we'll see what actually happened. And a lot of things happened during a period of 5 years, as you can tell, right? That there's a new model coming out every other week, whatever, right? So, but we'll see. But the key point is that we must also consider hardware embodied carbon, right, of that infrastructure. And I'll talk about the details later on to see where the carbon emissions are coming from. So finally, in terms of macro trends, I just wanted to, because this blows my mind, right? I just want to highlight here the capital expenses of the 4 hyperscalers, right? Or the top ones. This graph here shows over time on a quarterly basis, each of these bars is just 1 quarter. How much they're spending. And here you see this drop here. It was due to, if you remember, when we came out of the pandemic, all the hyperscalers were laying off people and cutting down costs and so on. So this is the drop here. But since then, you see this sort of really steep increase. And Microsoft has already Satya Nadella has already come out saying that we're going to spend $80 billion, just Microsoft, $80 billion in 2025 on capital expenses. So it's through the roof. Microsoft spent something like 60 billion in 2024. Those are crazy numbers. And you see here, I was talking about that period of time until 2018 and so on. The combination of them all was at $15 billion per quarter, right? 60 billion total. But the nice thing about this is that if the expenses are so high that any improvement that people who are here can make, even like a small thing, will pay our compensations for the rest of eternity, right? So it's an enormous opportunity to have impact, right? And not to mention the fact that if we improve this, it's not only lower capital costs, but also typically when you improve efficiency, it's lower power, lower energy, better sustainability, and so on. Okay. So where are we? Let me talk about, like I said, the three layers of the compute stack, starting with the physical infrastructure. And to illustrate, I'll compare cloud data centers with AI data centers, so you see how things are changing in that space. So we started out in terms of servers and networks in cloud data centers with your regular Ethernet and general purpose servers and so on. With the AI data center, we're adding accelerators, right, of different types for AI, including GPUs. And the network is also changing, right? The backend network is typically InfiniBand, although there's a consortium of Ultra Ethernet that wants to sort of replace the backend network with a more sort of Ethernet type of network. So big changes there. In terms of power density, cooling, and PUE, again, significant changes, right? Whereas for general like cloud data centers, you might see tens of kilowatts per rack in terms of rack power density. Now we're going to hundreds of kilowatts per rack, and there's no end in sight until sort of co-packaged optics come in. This thing is going to be growing, and we might have 1 megawatt per rack in a few years, which is mind-blowing, right? We started out like 17, 15, right? Just a few years ago. So in terms of cooling has been done for the most part with air and evaporative assist, right? That's the thing that sort of gets the PUE to be very low in most locations. In the AI data center, we're going liquid to chip, like cold plates on top of the GPUs or the other accelerators, plus air for things that don't need liquid cooling. And Microsoft, for example, has committed to not using water for evaporation anymore because water is a scarce resource. So Microsoft has committed to that. The other ones have not followed yet. We'll see if they follow eventually. But what that means is that PUEs are going to increase a bit, right? Because now you got water chillers, you got all sorts of things that will likely increase PUE. In terms of availability, typically a cloud data center is a 5 nines type design. And in some cases, you might see a combination of high availability and a bit lower, maybe 4 nines availability in the cloud. However, in the AI data center, you might actually see lower availability for training for sure, and maybe even for inference, because inference can tolerate a data center going down. You just reroute requests to some other stamp of your service. So finally, in construction costs, typically, I can't give exact numbers here, of course, but typically in a cloud data center, you see something like lower than $10 per watt. And in the AI data center, it's going to be a little more expensive because the chillers, the piping, and all of the stuff that liquid cooling requires. But so based on this, these changes, right, there are many sort of challenges coming up, right? One of them I mentioned already, right? The rack power densities just keep increasing. So think about it, right? You build the data center for 15 to 20 years, and then what you put inside changes every 6 months. How something's going to have to give, right? So we need to come up with better power delivery systems. So the PUE, like I mentioned, especially if we don't use water, will regress in warm locations. So we're going to have to work on better DC level cooling, data center level cooling. And the other thing that's happening is that utilities more and more want coordination with data centers, right? So some of them are already running out of power, and they might not have all the power that the hyperscaler needs to deploy a data center. But if the data center can shed some load during times of peak demand, when everybody's turning on the air conditioners and so on, maybe there's a way to provision it there at that location. So that was the physical infrastructure. Let me talk about hardware a little bit. Then I'll focus on NVIDIA GPUs, but you see the same thing in terms of other accelerators as well. So here on the x-axis, I'm showing 4 different versions of NVIDIA GPUs. The A100 came out in 2020. The H100 came out in 2022. B200 and GB200 both came out in 2024, right? So you're seeing this acceleration. And each of these curves is either power, performance in flops, FP 16 flops, and efficiency, performance per watt, right? So what you can see here is that in just 4 years, the power per GPU grew 6x, right? Luckily, performance grew by more than 6x. So efficiency has kept up. And in fact, efficiency is in a good trajectory, or was in a good trajectory until B200s. And then when GB200s came in, they took a dip because of the ARM CPU that's in every GB200 chip, right? And the chip is like one ARM CPU and two B200s, two B200 GPUs, right? So because of that, there was this dip, but hopefully, you know, it's not going to happen again, and we'll continue increasing efficiency. And the cost of these things is also like through the roof, right? If you look, and this is all sort of public information, right? So I'm not revealing anything. If you, according to the IT press, right? If you look at articles about this, a single rack of 72 GPUs with GB200s is going to cost $2.3 million or more, right? Again, crazy numbers. So what are the challenges here? Well, accelerator power will continue to increase fast. So we need to sort of bend this curve somehow. Keep increasing efficiency, right? It's one way to sort of mitigate that increase. This increase in power is going to require liquid cooling, right? When you have more than, say, 1,000 watts per centimeter square, you gotta go liquid cool, right? Because liquid is more efficient than air at extracting heat. And then the efficiency, like I mentioned, dipped down a bit, but it needs to start going back up again. Hopefully, I'm not going too fast, right? No, or not too slow either. So now, just to close that piece, let me talk about carbon emissions a little bit. And starting with the embodied carbon of different types of servers, right? So a CPU-based server, a GPU-based server, storage server based on hard disks, and a storage server based on a solid-state drive. And you can see that in terms of embodied carbon, the SSD server has actually got more embodied carbon than a GPU server, right? Which I didn't expect when we started doing this investigation. The interesting thing, though, is that when you account for the operational carbon, then the picture changes entirely, right? Because GPUs consume so much energy, right? That it really, when you add these two up, is much, much more than an SSD-based server. So the GPU servers emit the most carbon overall, and clean energy, of course, yeah.
Ricardo, is this over a time span of your expected lifetime?
Yes, over the lifetime
of the device.
Typically 6 years is lifetime.
Okay.
Yeah. So clean energy is going to help with this, of course, both renewables and nuclear. But there are many challenges, right? Sorry, I touched things in it. Okay. The operational carbon of the GPU servers is going through the roof, as I mentioned before. There's no common methodology for measuring embodied carbon. Even if everybody were to agree that we should do life cycle assessments, the scope, boundary conditions, high quality data, none of this is there right now. There's no agreement on how to measure this. So it's going to take some time until everybody agrees on how to measure this thing, and then we're going to have to start measuring across the board, right? And be able to compare and so on to be able to optimize. Another big problem is going to be what to do with previous generation GPUs, right? Because when one of these sort of super efficient ones, super fast ones, when they come out, nobody wants the old ones, right? So if there's another one coming out every 6 months, what do you do with everything else? All that carbon, right, is sort of we need to do something about it, right? We need to find ways to use those GPUs. And other accelerators too, right? It's not just GPUs. Okay. Now to complete the story here, let's talk about software, right? And I'll start with training. Training is a very, very interesting workload. So here I'm showing over time the normalized power training. As you can imagine, this is like highly sensitive data, so I'm not using any sort of scale to the axes, but you get the picture, right? So a few interesting things about this. Training is a batch job, right? There's no interaction with users or anything like that, but it's got high power utilization pretty much all the time. However, it's also a massively synchronous computation. Every GPU, and these are enormous. In fact, Google has come out publicly saying they use multiple data centers connected together to train a single model, right? All of these GPUs across all of these data centers work in lockstep, right? They constantly they run for a little bit, and then they communicate, run for a little bit, communicate, run for a little, right? So what happens is these enormous power swings, right? This here is a reduction of, say, 30% in the power, almost instantaneously, right? The problem with this is that this can destabilize the grid. right? One of these companies could actually bring down the grid. Well, hopefully the utility would shut them down before they actually bring down the grid, but there is a super challenge here, right? So all of the hyperscalers are figuring out how to sort of make sure that these big swings don't happen. And this is just a zoomed in image. It's like a huge drop and then a huge go up again, right? After the communication is done. Yeah.
Ricardo?
Yeah.
Do these happen because GPUs have to wait for each other, like you said, or is there another reason?
They're communicating, right?
I
So
see.
during the time that it's heavy compute, they consume an enormous amount of power.
Mm-hmm.
When it's low compute, it's just communication. The power goes way down, right?
I see.
And this is like
that's the
just
reason.
30%.
Yeah. Wow.
This can be more, it can be like 50% in no time at all, right? So it's not something that the grids are designed for.
Can I ask something too?
Yeah, of course.
Is this from the perspective of the grid? Like, is this the power demand on the grid, or is this just the demand of a single job from the grid?
This is just the demand from this data center, let's say.
Just one data center's demand from the grid.
Exactly, not what the grid sees as a whole. This is just from this data center. But just this one data center can bring down the grid.
Okay. So I was asking because, so from the grid's perspective, how big a change is this in the demand? And
Yeah,
actually, like how much does this grid, like the grid is supporting multiple things.
Yeah. Yeah.
Data center is one of them, and this data center fluctuates a lot.
Yeah.
But how bad is it from the grid's
No,
perspective?
the training data centers fluctuate a lot. Nothing else fluctuates a lot.
Mm-hmm.
Right? The training data centers are getting so large. There are data centers that are purpose built for training. We don't run inference in this data center. We only run training in this data center, right? Because the requirements for training are much more stringent than for inference. So because these things are so large, a jump like this causes an enormous problem. So every hyperscaler is working on this. The other interesting thing about training is that it's extremely primitive in terms of the handling of failures, right? I mentioned that every GPU is in lockstep, right? If one of these fails, or even a link flaps or whatever, the whole thing stops and restarts from a previous checkpoint. Now, think about this, right? Each data center is enormous, and you use multiple of them to do a training run. You will have something happen like that every several minutes. And taking a checkpoint and recovering from it is not instantaneous, right? So over time, the effective utilization of these things is going to go down. It is already going down because of that factor, right? The training jobs are the one type of distributed computation. They're so primitive. Every other distributed system is capable of making progress in the face of failures, right? But not this, right? So this needs work like immediately, right? And people are already looking at it. Of course, this is such a big problem that people are looking at it, but it's another opportunity there, right? There'll be lots of work in that space.
Can I ask one quick question?
Yeah.
Has there been a study that tries to estimate how much energy demand, or maybe not energy, but some other unit, maybe runtime, training time, would be reduced if we had somehow this hypothetical situation of no failures? Suppose there was no failure. Like how much of that training time is spent on actually recovery, some
Yeah.
kind of recovery from checkpoint logic.
Meta may have quantified that. Meta is the most open about this issue. Nobody else talks about it, pretty much.
Okay.
But there's a paper from Meta on this.
Okay.
Okay, so let's talk about inference, because inference is quite different, right? Inference is more like your traditional web service. But the interesting aspect of inference is that it's really two distinct phases, right? And this is, I'm talking about LLMs here, right? It has a what's called a prompt phase that's very computationally intensive. And there's a token phase that is memory bound. So you see here, I'm showing sort of power over time, and you can see that the prompt phases consume a significant amount of power, much more power than the token phases. And so some of the more challenging things here is how do you optimize for these totally different behaviors? And what I'll talk about in terms of our work is along those lines. And the other thing is maximizing power over subscription while staying within SLAs, which is what we regularly do for web services, right? We'll do it here too. So anyway, so these, hopefully this gave you a good view of the macro trends and what are some of the challenges across the compute stack. Now let me tell you about one work. First, I'll show you like a quick overview of some of the work that we've done in my group. We've looked a lot at the software layer and optimizations there. You may have seen some of these papers. In hardware, we're working with the different GPU vendors to bring their power management on sort of on par with power management in CPUs. We're sort of working on the power swings, right, stuff that I was describing before in training. In terms of physical infrastructure, we're looking at new cooling systems, new power delivery infrastructures, and then cross-layer, we're trying to work a lot sort of across layers, which is a source of opportunities there for sure. So what I'm going to talk about now is exactly on the inference issue, sort of how much benefit can we get from leveraging the different characteristics of the phases. So the name of this work, the name of the system is Splitwise. And what it tries to do is sort of recognize those differences, right? So on the left here, I'm showing the prompt phase, and on the right, I'm showing the consecutive token phases, right? The prompt phase processes all of the input tokens all in parallel to produce just the first token of the answer, right? So here in this, let's say this is a chat GPT chat, which is better, pizza or burger, right? And the token, the prompt phase, this is also called prefill, right? If you're not recognizing the names, it's called prefill and decode, right? These two. So the first token is going to come from the prompt phase, and every other token is going to be a serial execution of the token phase. You run one decode for each token that you produce. And I'm simplifying here, right? I'm assuming tokens equate to words, but it's not quite, just to simplify. So like I said, the prompt phase is compute intensive, power intensive, and the token phase is memory bound, much lower power. So the issue is running them on the same GPUs actually causes interference from all of the requests and all of the prompt phases of the requests, all of the token phases and so on. And because of this interference, the way things batch and so on, you got to over provision so that you don't exceed any SLOs and so forth, right? So a better approach is actually to seek a better match of hardware to software, right? So here I'm showing a small table on performance, power, and cost. And this is the ratio of H100 to A100. Okay, just to show you the difference, the different characteristics of these two generations of GPUs. And then let's look at what it's like to run prompt in H100s and what's like to run token in H100s in comparison to A100. So if I'm running the prompt with H100, you see here how much better it is than if I run with A100s, right? However, for the token phase, you see that the cost, for example, is higher to run it with H100s. And throughput is a little higher, but nowhere near the advantage in flops that the H100 has over A100. The energy per token is also larger, right? So why not? One possibility is, well, we split the phases, we run the prompt phase in H100s, and we run the token phase in A100s, right? So that's what we did. Splitwise takes, here's a simple demonstration of what it does, right? Typically, a GPU server will run the prompt phase, or a single GPU will run a bunch of prompt phases, a bunch of token phases. So what we do is we separate them out into two different servers. However, there needs to be communication between the prompt phase and the token phase, right? There's this thing called the key value cache that needs to be, basically the key value cache reflects how every token relates to every other token for every layer of the neural network, right? So this phase splitting requires this communication. And then, as you can see here, there can be a significant delay, right? Because the key value cache can be hundreds of gigabytes, right? So what do we do about that? Well, we essentially do pipelining, right? We start transferring the KV cache. As soon as the first prompt phase ends, we transfer the piece of the KV cache related to that phase over to the token server, right? And we keep doing this. And then you see that the only piece that doesn't get overlapped is the transfer of the last tier, right? The last layer. So there's a little bit of delay, but we've done experimentation with this and so on. And the increase in overall latency is only like 0.8% overall, right? So this works well. So just to show you a flavor for the results, right? And I'll go slower here to sort of, because there's a lot of information here, right? So these two are the two baselines, and I'm plotting normalized cost and power, okay? So this baseline is, I use all of my servers are A100s. Over here, another baseline, all of my servers are H100, right? And this is not split. The phases are not split. These other four here are split phase executions of inference. This here is, you split the phases, but you run both phases in A100s. Here, both phases run in H100s. Here we do a mix, like I mentioned before, right? Where prompt runs on H100 and token runs on A100. And this is one where the prompt runs in H100s. The token runs on H100s as well, but power capped, right? We cap it at 70% of the power. So if you look at some of these comparisons, right? If you compare if you simply split the phases. Don't change any hardware, no power capping, nothing. Splitwise already gives you like a 50% reduction in cost and power, right? Because throughput increased, and because throughput increased, you can use fewer servers for the same workload, right? Now, if you do a comparison of the H100 baseline with the power capped, it's still everything H100s, but the token phase is power capped. You get an improvement of 25% in terms of power, right? Power goes down by 25%. And if you compare the two approaches to this heterogeneous execution, using two different GPUs is cheaper, right? It's a bit cheaper than this, but it spends a little more power, right? So hopefully this gives you sort of a view of the benefit. Number one, it's great to split, even if you use the same GPUs. Number two, if you introduce some heterogeneity, you can actually do even better, right? And then which type of heterogeneity you bring in depends on what you want to optimize, whether it's cost or whether it's power. Okay. So hopefully that gave you a sense for the kinds of things that my group is looking into, is like when you do inference, what efficiency optimizations can we make? But let me talk about the other things that I think are sort of still open and good opportunities. And my group is looking at those too, but other opportunities that are ripe for the taking by different teams. So there, in my mind, you know, every group is doing, if you're a software group, you're doing these kinds of things that I just described. If you're a hardware group, you're looking at, you know, accelerators, you know, quantization and that kind of stuff. If you're physical infrastructure, you're looking at, you know, cooling and so on. So everybody, in my mind, is working within their silo, mostly, right? There are some folks that work across the stack, but that I think is a big opportunity, right? There's like cross-stack optimization. The first thing in my opinion, we have to do is to rethink the AI stack from a different perspective, right? Instead of thinking only performance per TCO or performance per cost as the metric to optimize, it should be more like performance per watt, performance per watt hour, in the case of energy, or performance per carbon emissions. What's interesting is that depending on which metric you pick, you design different things, right? So if you decide to optimize for power, we'll do something. If you decide to optimize for energy, it's a different design, right? Which is very interesting. And then there's a more sort of general question of how do we modify systems engineering, right? Because systems engineering is typically siloed, so teams can scale and so on and be able to build systems in an easier way, right? So it will take some thinking there, right? I'm also very interested in cross-stack design, right, for maximum efficiency. The trick is, like, the search space is very large, and where do you start, right? You sort of have to say, oh, let's assume this, and then design from that, right? But what is this? It's up for grabs, right? Nobody knows what sort of the base of this search should be. Maybe the accelerator is one option. But there's scope there for a new methodology. The notion of sort of cross-tier design between software and physical infrastructure is also very interesting to me. We have a big effort on software-defined data centers here, where we took over sort of the control of power, the control of repairs, the control of performance that's given, and all of these things. We're working on many of these. And especially the aspect of grid interactions, right, that I mentioned before. So sort of the notion of power modulation to be able to interact with the grid when the grid needs it. Say the grid needs you to sort of shed some load to for it to be able to regulate frequency, or even increase the load for it to be able to regulate frequency, especially as more and more renewables come in, right? So the notion of provisioning additional batteries and additional generators for becoming transparent on the grid, right? Where, say, during hours of peak electricity consumption, the data center sort of turns on its generators, say, right, to reduce that load. Those are examples of things that may come to be needed very soon. So in terms of single layer opportunities, I think like in the 3 layers, there are many opportunities for improvements. For example, safe power delivery at increasing densities, like I was mentioning before, right? Trying to make the power delivery infrastructure more modular somehow, right? So that racks that consume a lot sort of bring their own infrastructure and so forth. New cooling technologies where maybe we bring liquid through the chip as opposed to just on top, right? Would be a way to enable much higher electricity consumption, much higher throughput and so on from a single server, so that we need fewer servers. The problem of curtailed renewable energy, I don't know if you know this, but a large percentage of the renewable energy that gets produced is thrown away, right? Because the grid that is connected to that installation might not be capable of absorbing that electricity at times. So there's something like 10 to 30% of renewables that just go wasted, right? Finding ways to take advantage of that electricity, right? By maybe deploying data centers with the wind farm or with the solar farm. Of course, the trick is that there would be greater unavailability that typically one is used to, right? Because things change on a daily basis. So that's another problem that is ripe for study. And some people have studied this, by the way, right? The curtailed renewable energy has been a topic for Andrew Shen in Chicago, for example. He's looked at that a lot. In terms of hardware, like we said, right? Accelerators, new networks, a lot of people looking at disaggregation, right? Those kinds of things. I mentioned co-packaged optics before, right? And finally, in terms of software, awareness of power, or awareness of energy, awareness of carbon, when we design distributed systems, right? And the other one that I mentioned was sort of more less energy intensive approaches to fault tolerance in training, especially, right? Or is also a good opportunity in my view. Anyway, so these are just some things that I find interesting, that I think are potentially interesting areas for further research. So just to conclude, I think we're right on time. The AI era is just beginning, in my view, right? Everything that's happening is just the beginning of this whole phase. And there's huge demand for capital, huge demand for resources, but it's a huge opportunity, right? We're living in a extremely interesting times, right? So awesome opportunity for research in this space. But we need all hands on deck, right? It's not just the hyperscalers. We need everybody who's interested in this topic to contribute. And because of that, we keep putting traces out there. If you search for Azure public data set, you'll find we got data sets up the wazoo over there, right? Like, I think we have like 7 sets of data from VMs, from functions, serverless functions, on AI as well, sort of power traces and all of that stuff. It's all there. So we want everyone, right? Academics, practitioners, everybody to join the fray here. And the other link is a link to my own research team. Anyway, so this is what I had. I have a little more time if you want to go a little longer. Happy to take questions. Hopefully this wasn't too much. I wasn't sure.
This was great. Thank you so much, Ricardo.
Of course. Thank you all for attending.
May I ask a question?
Of course, yeah.
Actually, you mentioned something about this stabilization, sharp decrease in the amount of power consumption. Does it mean that we should, of course it is somehow maybe ridiculous, but does it mean that we should increase the amount of energy consumption in that point in order to stabilize it? What is the common solution for these cases?
Yeah, I can't say too much, but yes, that is one aspect that people are looking at as a short-term solution. But people are also looking at other things like batteries, capacitors, right? Because nobody wants to sort of raise that floor and waste energy just so that they don't bring down the grid, right? There should be other sort of techniques